Okay, let's do one more diode problem before we look at common diode applications. So here in this circuit, we're going to treat the diode as ideal as we've been doing. Later on in the quarter, we'll see how to analyze circuits where you're treating the diode as actual. And we want to find what that diode current is, what the ideal diode current is. So to do that, we need to find, well, is this diode forward bias or reverse bias? Because if it's forward bias, then we're going to have current flowing from anode to cathode. If it's reverse bias, then our answer for diode current would just be that it's ideally zero, since an ideal diode acts as an open when it's reverse bias, and it acts like a short when it's forward bias. So we're going to use the ideal diode model as we've been doing in previous videos. Okay, so remember, this is where you make a reverse bias assumption, and then we do some analysis, namely find VD. Okay, and VD is the voltage across the open that represents the reverse bias diode. So we're doing analysis to either prove or disprove this reverse bias assumption. So we just need to find voltage on both sides of this open. VD from the model, the way it's defined is that the diode voltage is VA minus VK. So if you look right here, all that's between node K and ground is this 10 volt source. So VK is just 10. Alright, and to get VA is this voltage on this side of the open, which with respect to ground is the same voltage across this 3K. Okay, so VA is just equal to the voltage across the 3K ohm resistor. And since current is only flowing in this path here, right, single path for current flow, so these resistors, the 1K and 3K, are in series. So I can use voltage division. Okay, voltage divider equation to find that voltage. It's just going to be the 20 volts times 3K over 4K. So our VA is 15 volts. So our diode voltage is 15 minus 10, which is 5 volts. So our conclusion is that our reverse bias assumption was incorrect, that this diode is forward bias. And therefore, since it's forward bias, it's acting like a short. So to find the current, okay, to find the current for this forward bias diode, we replace the diode symbol with a short. And remember, the left side here, that was the anode. The right side here is the cathode. So our forward bias current always flows anode to cathode. So this is the actual direction of our diode current. So one way we could find that diode current is by mesh analysis. We could define a mesh current here, I1, mesh current over here, I2, write our KVL equation, solve our simultaneous equations, and whatever I2 came out to, that would be our diode current, okay, our forward bias current. Instead of that method, I'm going to just look at the nodes, okay, do a nodal analysis. Okay, this is our ground node where voltage is defined to be 0. And this node here, okay, which has the 20 volt source connected to it. And since all that's connected between these two nodes is that voltage source, we know there's 20 volts at this node with respect to ground. And likewise, we know that there's 10 volts at this node with respect to ground. So when you do a nodal analysis, you find that all these nodes are known, all the voltage, the node voltages are known. So we can find the currents using Ohm's law. So this current here through the 1K, well, that's just going to be 20, the voltage on the higher voltage end, right? Remember, current flows from the higher voltage end to the lower voltage end through a resistor. It's always absorbing power. So we have 20 minus 10 divided by 1K. Okay, so that's 20 milliamps through that 1K. And then for the 3K, we're going to have 10 minus 0, the voltage across the 3K divided by 3K. No, actually, I made a mistake here, didn't I? It's 20 minus 10, so this is, sorry about that. This is 10 milliamps. Okay, obviously here, 10 divided by 1K. And then our 3K current is just going to be 10 divided by 3K, which is 3 1/3 milliamps. So now by KCL, the current through this short, which is the same current as the 10 volt source current, since they're in series, well, ID is just going to be the current through the 1K, 10 milliamps, minus the current through the 3K, right? Because we know from KCL that currents at a node have to sum to 0, right? Currents in equals currents out, so here's my current in, and I'm subtracting one of the currents out, so I get the other current out, which is the same as the diode current, again, since they're in series. So that's our answer, is that our forward bias diode current for this example is 6 2/3 milliamps. Alright, so we'll talk about some common diode applications next, and then we'll get into analyzing circuits where the diode's considered non-ideal. In fact, we'll come back to this problem and analyze it again, treating the diode as non-ideal.